Hello everyone! If you look at the butterfly or starfish apart from their pretty colors, a unique feature that stands out is their symmetry. Similarly, engineered systems like buildings, airplanes, or cars have a symmetrical shape. Designers usually take advantage of symmetry when they create models. Only a portion of a symmetric model needs to be modeled, and modeling tools such as mirror or copy of the section can be used to generate the entire model. Can analysts also take advantage of symmetry while analyzing symmetrical structures? The answer to this question is yes. In this video, we will discuss when it is beneficial to impose symmetry boundary conditions to make the analysis more computationally efficient and accurate. On the other hand, we will point out the situations when symmetry boundary conditions should not be used. This video will consist of a short lecture followed by a walkthrough example using Ansys Mechanical. Ready? Let's get started. A commonly asked question is, how can we utilize symmetry in our analysis? Some analyses may require large amounts of memory and computational time to obtain a solution. If the geometry, material orientation, loading, and expected response are all symmetric about the same planes, we can take the advantage of planar symmetry and only model a portion of the actual structure to reduce the analysis runtime and memory requirements. Also, a finer mesh can be used in a symmetry model, resulting in a more accurate solution than a coarsely meshed full model with similar number of nodes and elements. In solid mechanics, the general rule of a planar symmetry boundary condition is that the component of displacement normal to the plane of symmetry should be set to 0. This makes sense if we think of symmetry plane like a mirror, as the deformation shouldn't move into the mirror or overlap onto itself. For line and surface bodies, another requirement is that rotations in the plane must also be constrained. Using the mirror analogy, a structure shouldn't rotate into the mirror. Although there are several types of symmetry boundary conditions available in Ansys Mechanical, we will focus our attention in this video on the Symmetry Region feature, which is used for planar symmetry. The symmetry region can be defined based on either the global or local coordinate system, where we specify the symmetry normal direction. It is worth noting that for 3D solid bodies, instead of symmetry region, a frictionless support can be applied on the face laying on the symmetry plane, since a frictionless support also constrains translations normal to the face. However, frictionless support can be used as a replacement for symmetry region for line or surface bodies, since in-plane rotations will not be constrained with frictionless support. Note that magnitude of any applied force laying on the planes of symmetry must be properly adjusted. For example, in a half-symmetry model, only half of the magnitude of force should be applied if the surface crosses the plane of symmetry, since we only have half of the geometry modeled. Note that no adjustment of magnitude is needed for pressure, gravity, or temperature loads. After solving, the results from the symmetry model can be visually expanded about symmetry planes to show the full model, which is useful when presenting your results to others non-familiar with finite element model. So, why should we use the symmetry boundary conditions? A big reason is that analysis can be more accurate. Since the size of the geometry is reduced, a finer mesh density can be used compared to a full model, which will result in a more numerically accurate solution compared to the full model with the same number of nodes and elements. The results of a quarter symmetry model can be visually expanded to represent the full model results. In mechanical, visual expansion of the symmetry model results is beta feature that needs to be turned on under Options, Appearance, Beta. In the Details view under Symmetry in the tree outline, the number of repeated symmetry segments needs to be defined along with a small overlap value in the symmetry normal direction. If there are two planes of symmetry, then two graphical expansions would need to be defined for each symmetry plane. Let's get back to the last question about symmetry region or planar symmetry. When shouldn't we use the symmetry region? If any of the four requirements, such as geometry, material orientation, loading, and expected response, are not symmetric, a symmetry region shouldn't be used. For example, in a dynamic analysis like modal analysis, a symmetric structure can have non-symmetric modes, and using symmetry makes us miss these modes. Another example is linear buckling analysis, where using a symmetry model will omit non-symmetric buckling modes. However, for typical stress analysis, utilizing a symmetry region is usually beneficial when all of these four requirements are met. Let's now see how to set up, solve, and post-process symmetry model in our walkthrough example in Ansys Mechanical. For this walkthrough session, let's consider a model of a flange joint. A flange joint consists of two flanges connected with the nuts and bolts. If we take 1/6 sector of the model and copy it around central axis, we can generate the complete model. So this flange joint model can be considered as a symmetric model. Let's look at the loading on this flange joint. Let's assume that the fluid flowing through the inner region of the joint is exerting a uniform pressure on the flange. Next, let's also assume that uniform force is acting on the top face of the top flange. Let's also assume that all bodies of this flange joint are made up of structural steel, which exhibits isotropic material properties. The geometry, material orientation, loading, and expected response all exhibit symmetry about the same planes. Thus, we can take advantage of symmetry and model only 1/6 sector of the full model. This will not only help to reduce the analysis runtime and memory requirements, but also get more accurate results. To model this 1/6 sector of joint as a symmetric model, we could make use of the cyclic symmetry region. Recall that cyclic region allows us to solve for repeating sectors and still get a non-symmetric response. Cyclic region is a repeating pattern, so it allows for twisting. However, symmetry region is a mirror about the two planes, so there is no twisting. Hence, for this example, as we are expecting symmetric behavior for each sector, we will use symmetry region instead of cyclic region. Now that we have finalized on the type of symmetry that we would be using for this analysis, let's create the 1/6 sector of the flange joint. Let's start with the flange model having bolt connections simplified in the form of beam elements. Open a new session of Ansys Workbench. Drag and drop static structural system on the project page. Right-click on the geometry cell and import flange model. Now double-click on the geometry cell to open and import geometry. We first need to create the symmetry planes for splitting the geometry. Select the x-axis from the global coordinate system and click the plane tool. This will create a plane along YZ plane. The plane is passing through the bolt location, and we would not like to create the section which cuts the bolt's location, so let's rotate this plane. As there are 6 bolts location, the angle between 2 bolts is 60 degrees. We need to create a plane that is in the middle of the 2 bolts locations. So we need to rotate the plane by 30 degrees. Using the Move tool, we can rotate this plane. Now we need to create another symmetry plane located at the angle of 60 degrees from the previous plane. Select the Move tool again and select the plane. Press Ctrl key and drag the plane along the curved red colored axis. Then type 60 degrees. We now have the 2 symmetry planes for splitting the geometry. Select the Split Body tool, Then select both the flange bodies and select any one plane for splitting the selected bodies. Now select the cutter tool from the tool guides and select the second plane for splitting the geometry. The 60-degree symmetry sector is now separated and ready for further use. The remaining bodies are not of interest and can be suppressed. The symmetry model can now be transferred to Ansys Mechanical for performing the simulation. Close the window and double-click on Model cell to open Mechanical. As mentioned earlier, all bodies are assumed to be made up of structural steel. Let's proceed to defining the contacts. It can be seen that one contact has been automatically created between two flanges. Let's change its properties. First, let's change the contact type from bounded to frictional contact. Set the frictional coefficient as 0.1. Leave the other settings to their default values. We need to create contacts for connecting the beam elements, which represent the bolt, with the flange. Insert a manual contact region. For contact geometry, select one end of the vertices of the beam. And for the target geometry, select the annular face of the flange located on the same side of the vertex selected earlier. Let's keep the contact type as bounded. Change the formulation to MPC and constraint type to distributed, all directions. Select radius option for pinball radius and specify radius of 6 mm so that the annular face falls within the pinball region for contact detection. Similarly, create a contact on the other end of the beam. Since we will be using Symmetry Region for defining symmetry, we first need to create local coordinate systems with the same orientation of the symmetry faces. Right-click on the coordinate system tree and insert a new coordinate system. Select any side face of the flange located on the symmetry plane to create a local coordinate system. To ensure that two of these axes are parallel to the selected face, go to Principal Axis Selection and change the Defined By option to Geometry Selection. Select any straight edge on that face to match the axis with the face. Similarly, create another coordinate system on the other symmetry plane of the model. Now comes the main feature that needs to be defined for simulating this symmetric sector. Right-click on the model tree and insert Symmetry. Right-click on Symmetry and insert Symmetry Region. Select the two faces of the flange located on one of the symmetry planes. Next, select the coordinate system that was created on this symmetry plane. The symmetry normal should match the axis of the local coordinate system in the direction normal to the symmetry plane, which in this case is the z-axis. So select the symmetry normal as z-axis. Similarly, create a symmetry region for the other symmetry plane. Let's define loads and boundary conditions for this symmetric model. Let's first add a bolt pretension load on the beam. Generally, pretension load is applied in two load steps. In the analysis settings, change the number of steps to 2. Now add a bolt pretension load. Select the edge of the line body as the scoping geometry. In the tabular data panel, specify preload as 1000 newtons in the first load step. Then log the second load step. Details on bolt pretension loading can be found in a separate course. Next, add pressure load and select inner cylindrical faces and apply a pressure of 1 megapascal in the second load step. Add a force load on the top face of the top flange. select the Define By option as components. Then go to the tabular data and specify 500 newtons along the Y direction in the second load step. Lastly, let's constrain the bottom face of the bottom flange using frictionless support. The model is now ready to be solved. Before doing so, let's add a couple of results, mainly total deformation and equivalent stress. The solution completes in a few seconds, and you can check out the deformation and stress contours in the model. While presenting the results of a symmetric model, it can be helpful to expand results to show the full geometry. This can be quickly done using beta functionality of Symmetry. To enable beta features, go to the Workbench project schematic. In the Tools menu, select Options. In the Appearance selection, enable Beta Options. Since this model is repeating in a circular pattern, we need to create a cylindrical coordinate system for expanding the results of Symmetry model. Add a new coordinate system and change its type to cylindrical. The z-axis of this coordinate system should align with the axis of the symmetric model. First, select any circular face to position the cylindrical coordinate system on the axis of the model. Now add rotation around x-axis and specify rotation angle of 90 degrees. Click on the Symmetry folder in the model tree. In the Graphical Expansion 1 section, specify number of repetitions as 6. Select the type as polar. Specify sector angle as 60 degrees. Lastly, select the cylindrical coordinate system. You can now visualize the results of the full model. If you recall from the lecture, we use symmetry to make the analysis more efficient and accurate. Let's look at the results of the symmetric model and full model for a finer mesh resolution. It can be seen that for a particular mesh resolution, the symmetric model solved about 10 times faster than the full model. Thus, you can obtain a more numerically accurate results on a symmetry model by using a finer mesh, yet the solution can still be faster compared to the full model. This completes the demonstration of how to use Symmetry Region in Mechanical. Let's summarize. It's advantageous to use symmetry when geometry, material orientation, loading, and expected response all exhibit symmetry about same planes. Using Symmetry Region can give more accurate and more computationally efficient solutions. However, the Symmetry Region should not be used when all 4 symmetry requirements are not satisfied, such as in modal or linear buckling analysis where non-symmetric modes need to be calculated. I hope you found this video informative. Thank you for watching, and check out our other courses to discover more useful learning resources.